experience. There's, of course, what's going on in the body, the physiological response, our sensory systems, the brain processing. But then there's also the experience that we have of that. And the way that we try to study this last thing, the phenomenal experience of the world scientifically, is to look at the way there are systematic correspondences or mappings between the world and the body and experience. And so a technical term here is isomorphism. I'll try not to use that technical term. So how would this work for the case of color? So when we're thinking about the world, when we're looking out at the world and there's surfaces that have colors, we describe that scientifically by referring to the percentile of wavelengths of the visible spectrum that get reflected from a surface. So each surface has a spectral reflectance profile. And when we think about this geometrically, it's actually an infinite dimensional space because we think that wavelengths of light can change continuously. I can say more about that if people are interested. What's going on when we think about the body and the physiology of color perception? Well, we have cone receptors in the retina that respond differentially to different wavelengths of light. And then those cone receptors are wired into opponent circuits. And there's a kind of geometrical space of neural activation. And then we're thinking about experience, phenomenal color space, by using the methods of psychophysics, which varies the physical stimuli in order to see how the psychological experience changes. We can study that and build models of that, and many of the models of color experience are three-dimensional. So here is my attempt at kind of depicting how these things fit together in a kind of heuristic way. There, with the color of the apple and the greenness of the leaves, you have different surfaces with different surface spectral reflectance profiles. We can ask, on the one hand, how those different patterns of wavelength of light are processed by the cells in the retina and the lateral geniculate nucleus in the body and the brain. We can ask how they influence our color experience as measured through various types of color relevant behavior. And then there's an assumption that that model of experience and that model of neural activity will be somehow structurally the same. And then I think that this general pattern is going to be a pattern for studying any kind of perceptual experience, including smell, including sound. And what I want to do now is focus a bit on this thing, the quality space, the space of possible color experiences. What is that? What background assumptions do we have when we talk about this as a way to study phenomenal experience? So this term quality space and quality space theory is not introduced by me. David Rosenthal is a philosopher of mind, famous for talking about quality space theory. Austin Clarke has an influential book where he talks about this. The basic idea is that a quality space is a geometrical arrangement of phenomenal qualities in a single sensory modality. And it has, importantly for our purposes, two kinds of structure. So these are technical geometrical words, but it has topological structure. That just means the nearness relations represent perceptually close relations. So colors that are similar will be close to each other. But then also, ideally, not just this topological, this neighborhood relationship is represented, but also there's metrical structure. There's distances between points that correspond to distances in experience somehow. So I'll say more about how we might get that. But the basic idea of quality space theory is that the percepts from any modality, so color, loudness, pain, hot and cold, whatever, may be arranged geometrically such that this geometrical arrangement characterizes all the possible qualitative experiences you might have in that sensory modality. And I would claim or endorse the claim that once you produce a geometrical arrangement of possible phenomenal experiences this way, then you have a kind of object that can be studied intersubjectively through the methods of science that will, to some degree, explain the qualitative character of our sensory experience. So normally we think of the qualitative character of our sensory experience as being only available to us subjectively, but quality space theory finds a way, provides a way of taking that subjective thing and making it intersubjectively available. If there's questions about that, we can talk about that in the question period. So just to say a little bit more about these quality spaces for color, here's one example, the Munsell color space. And this is an attempt to arrange possible color experiences in steps that are kind of perceptually equal along 3 different dimensions. So there's a vertical dimension of lightness and darkness. There's a dimension of degree of saturation that comes out from that central kind of neutral core. And then hues, the different types of colors sort of go around the outside circle. And the Munsell color space is constructed so that each of these steps is meant to be of the same size in terms of your subjective experience of it. So they're perceptually equal steps, but these 3 different axes are not comparable. So equal steps of lightness, equal steps of saturation, equal steps of hue, but you can't talk about meaningful distances diagonally through the space. You can't compare the steps of value with the steps of saturation. An example of a different, more sophisticated space at a later stage of color science, the Scilab space, is an attempt to now have do the same thing, have perceptually meaningful increments of distance within the space, capturing all possible color experiences. But now, to say that it's isotropic means to say that the distances in any direction can be compared. So now diagonal distances are meaningful. So I said that very quickly, but we can come back to it. But my view about how we might scientifically study phenomenal experiences to construct objects like this. So this brings us to the topic of measurements, because if I'm claiming we can study subjective experience of phenomenal qualities through constructing these quality spaces, then the question is, well, where do we get them? And I think them through acts of measurement. There's a lot to say about measurement. It's one of my research interests. I will try and say only a tiny bit here, just enough to make sense of what's going on in this area of science. So I'm going to define measurement for the purposes of this talk as an empirical procedure for assigning points in a metric space to states in the world. That's actually maybe a controversial definition, because normally when we're thinking about measurement in the physical sciences, all we care about are assigning states of the world to numbers, normally positive real valued numbers, if you're thinking about something like length or mass or temperature. But that's really just a special case of assigning states of the world to points in a metric space considered more broadly. So the real line is just a special kind of metric space. And what do I mean by a metric space? A space that has this structure that I mentioned earlier, metrical structure. That means distances within it are well defined. So how's it going to work for color? Well, here's a setup for an experiment for studying color, and in particular for looking at the relationship between something like surface spectral reflectance and phenomenal experiences of color, by looking at cases where different patterns of wavelengths of light are perceived as identical by the subject. And so what you have, if you look on the right-hand side, is what the subject views. They see a field with kind of 2 sides to it. And on the left-hand side is sort of from above, you can see the subject standing in front of this little hole. And on one side is the test light. That's a light that can have any distribution of different wavelengths in it. And then on the other side, there's 3 different lights that can be set in a variety of different ways, but they have a much more restricted set of wavelengths. But if you set those 3 lights in the right sort of way to be sufficiently different, then it turns out the subject can adjust the strength of those 3 lights until the line in the middle of their visual field disappears, and the field that they're looking at looks a homogeneous color. And so you've matched these 3 test lights, these 3 primary lights, to this test light of a very complex spectral power distribution. So this is a setup for an experiment that's measuring something about how people perceive color. And what do you get out of an experiment like this? You get a mapping from the visible range of the electromagnetic spectrum into 3 dimensions. And this picture here is a kind of two-dimensional slice through this map where it's a plane of constant brightness. And geometrical representations like this have been produced in color science since the early 20th century. This particular one was a very important one by this International Commission for Studying Color called the CIE 1931 Color Space. And this is part of the way towards scientifically constructing a quality space. But why is it only part of the way towards constructing a quality space for our experiences of color? Well, it's leaving something out, because when I said we were trying to measure color, we weren't just trying to measure the layout of different possible color experiences. We also wanted to have meaningful distances between color experiences in that model. And this procedure, this experimental procedure, gives you topological relations between possible color experiences. It tells you which ones will be nearby and how they will vary as the physical stimulus varies. But what it doesn't tell you is, will two different color experiences seem close to each other or far apart from each other? There's no distances over it. But there are ways to measure distances. So once you have this arrangement of possible color experiences, you can measure distances within it in a variety of ways. Here are data from two different sort of early experiments measuring distance within it. The one on, maybe I'll just talk about one very quickly so we can move on to smell here. But the one on the right where you see these lines in that space that has the same shape as the CIE 1931 standard observer. Where those lines came from is the subject was sitting in front of a screen, very much like the initial experimental setup I showed you. But now they were only able to adjust one pair of lights to ensure that any adjustments they make were on a single line. And they were supposed to adjust one side of the screen so it looked the smallest possible difference that they could actually identify, first in one direction and then in the other direction. And so each one of these lines stands for kind of two increments of just noticeable difference. And if you think that a just noticeable difference should be everywhere the same size, then what it shows you is how to take the CIE 1931 observer and distort it so that distances within it now become meaningfully comparable. So that was probably too fast. We can come back to that, but it's kind of important for talking about the study of phenomenal experiences of color as genuinely measurement, in my view. I'm going to rush a bit now to get to talking about smell, so we can talk about smell a bit more. But I want to make one more point about measurement in general, which is a procedure like this for putting numbers or a geometrical representation on the states of the world. There's always a risk that in devising that procedure, you've somehow illicitly smuggled in assumptions, or you've set up the procedure in such a way that it's kind of creating those numerical assignments rather than discovering some sort of quantitative structure in the world. And this is a big problem that there's lots to say about. But one thing that will become important later when we talk about smell is you get reason to think you're starting to latch onto something that's really the correct description of the world if you have different measurement procedures, which then converge in the sense that they assign the same outcome when you target them at the same quantity. So in the case of measuring temperature, for instance, I can measure temperature with a mercury thermometer, which relies on the physical process of the expansion of a fluid with changes in heat, or I can measure temperature with a thermocouple that relies on a physical phenomena whereby the electrical activity between two different kinds of metals changes with the change in heat. And so different physical phenomena, if they're converging on the same value for a temperature, that gives me increasing evidence that I've latched onto some real structure in the world, I think. And so in the case of building our quality space for phenomenal experience of color, if different procedures for measuring color converge on the same geometrical structure, that counts as increasing evidence that we're really latching on to the kind of the true description of color experience. And I'm going to, at the very end, apply this criteria to try and make the argument that maybe smell space is 6-dimensional. So we'll see if that makes sense. Because of time, I'm going to skip this point, which is about convergence in color science through a different kind of data. We can talk about that in the questions if we want. Okay, so smell. That was all color. That was all color. Let's talk about olfaction and the experience of smell. So remember I said, if we want to study perceptual experience scientifically, we need to consider 3 different things: the world, the physiology going on with the body, and the phenomenal experience. And if we think about smell, this starts to look much more difficult. So we know that when we're smelling things, we're smelling volatile chemicals, molecules that are floating around in the air. Okay, but what is the feature of those molecules that's relevant for determining how they smell? It's not obvious at all, and different theories about that. There's different theories about that. Now think about the body. In the case of color, where we had this very small number of receptors in 3 types of cone cell in the retina. In the case of smell, there's around 400 different kinds of odor receptors in humans, and they project to the olfactory bulb where they're initially processed in a very complicated and distributed way that we don't understand very well at all. If you think about trying to understand what our phenomenal experience of odor is like, even independent of this question about the world and the body, we're actually in a quite different place than we are with color, because with color, we have a very rich vocabulary for talking about colors. We have a long history of art that employs color and that developed a whole theory of how colors are related to each other that we can employ. And so there's a lot of kind of folk phenomenology, folk theory about color experience. And now this is interestingly one of these issues that may be cross-culturally different, but certainly in the English-speaking world, there is not a very rich vocabulary for talking about odors. Most of the words that we use to describe odors either refer to the thing that has that odor to say that it's similar to that. So I don't know, smells flowery. Well, that's making a comparison to the way flowers smell, right? It's not a word that's about the odor by itself. Or it's some kind of metaphor. So my partner was making coffee and it smelled burnt to them. Well, it's not so much as if the coffee had literally burned. It was more that kind of metaphor with how burning things smell. So all of these features make it difficult to scientifically study smell. So here is a diagram from a paper by Malnick et al. To try and illustrate some of the problem here. Over on the left side, you have descriptions of different volatile molecules, odorants, that from the standpoint of chemistry look very, very, very similar. Across the top, you have different odor receptors in the nose graph, and you have an indication of whether or not they're triggered when this molecule is floating through the air. And quite different sets of them you can see respond to these molecules that look chemically very similar. And over on the right, you have qualitative descriptions of what the odors are like. And you can see, for instance, the first one, rancid, sour, goat-like. The second one, sweet, herbal, woody. Seemingly tiny change in the molecular structure has resulted in a quite radical change in the phenomenal experience of that volatile molecule. So this makes it very difficult to do what you do in that color experiment that I showed, where you're sort of systematically varying the thing that we know is the physical stimulus for color to see how the person responds. It doesn't look like there's a clear way to systematically vary the chemical structure of the odorants and get some nice nearby smooth trajectory of changes in odor experience. Nevertheless, there is a long history of people trying to come up with quality spaces for olfaction. So an influential one by Hans Henning, German psychophysicist in the late 19th, early 20th century. He has an odor prism. So the way to understand this diagram on the left is that it's only on the outer surface, the three rectangular faces of this odor prism, that smells are supposed to lie. And he came up with this by, he had some reasoning that there were these axes of opposite kinds of smells to form the triangles at either end. But a space like this turned out to be woefully inadequate. There are smell experiences we can have that don't fit within it. There are distances, seeming differences between smell experience that don't sort of quite match onto it. On the right, you have another attempt at sort of geometrically organizing smell experience coming from a very different tradition, from the tradition of perfumery. So there's a many hundred years tradition of people creating artificial scents for people to wear for aesthetic purposes. And that tradition has built up a very rich vocabulary for talking about smell experience. And so that's the origin of this diagram. But crucially, neither of these diagrams have the features that we wanted of a phenomenal quality space in terms of capturing all smell experiences, getting the topological relations between them right, getting the nearness relations between them right, and they certainly don't have, on top of that, a meaningful metric structure or meaningful distances between smell experiences. Okay, so just to summarize, in the case of color, we know what the relevant physical properties of the stimulus are, so we can vary these systematically. And as we do this, we've been converging through our study of the physiology and our study of the phenomenal experience on these kind of three-dimensional representations. In the case of odor, we don't know what properties of the stimulus are relevant, and so we can't start to understand phenomenal odor space by systematically varying the stimulus. And the physiology also doesn't seem to really help us. It seems too complex. We don't understand it well enough. So what do we do? So how do you measure smell? Well, there are data sets about different kinds of olfactory experience. And how do they work? So I'll say a bit about this first one I list here, Dravniak's Atlas odor character profiles. This is an atlas in the sense that it's a list of different kinds of different specific volatile chemicals. And then each one of them has an odor descriptor attached to it. That's a description in words of English about how it smells. And the way that this atlas was constructed is 160 odorant molecules were picked. The subjects were people working in either the food industry or the perfumery industry, or they were scientists who specialize in the study of odor. So they were all basically experts who, for one reason or another, were studying odor or taste or things like this. Through a pre-sorting process, 146 different odor-relevant adjectives were chosen. And so each subject received the sample of the odorant, and then for each of these adjectives, they gave a kind of percentile ranking of how much they could smell. They would apply that adjective to that odorant on a scale of 0 to 5. Now, what that gives you, it is a kind of geometrical smell space. We don't know that it complete and includes all phenomenal smell experiences because it's really just derived from these 160 odorant molecules. It has 146 dimensions. Why? Because each smell stimulus is placed in a space that has an axis, these odor-relevant adjectives, and it's given a quantitative position through this ranking of 0 through 5. So it's put all of these 160 odorant experiences in this 146 dimensional space. I thought I'd quickly show you what a page from this atlas looks like. So it starts with a description of the odorant, what the chemical structure of it is. But then the interesting part here starts halfway down where you can see the list of the descriptors. So these are the words that have been pre-chosen. And so some of them here, like grapefruit, you see nobody thought that this applied at all to this particular chemical. Fruity other than citrus had a few people applying it. If we go look further down the list, you see some of the other words chosen, things like oily, fatty, paint, varnish, fried chicken, sweaty, rancid, sulfidic, garlic, onion. And so terms like, for this particular chemical, sweaty, and if you go further down, light and sickening, all received relatively high. So these numbers are just kind of the percentage of people who, some sort of weighted average over the numerical assignments that people gave on that particular adjective. So higher numbers mean more people use that adjective or assigned higher numbers to that adjective. Okay, so, but what would you do with something like this data set? So now we have a data set that really is about smell experiences, in the sense that it's derived from the words that people are using to describe what it felt like to smell that smell. And it's got a kind of match between these qualitative descriptions of smell experiences and these physical stimuli. It's got a lot of dimensions. It's got 146 dimensions. And also, those dimensions are completely arbitrary in some sense. It was just these words were chosen by the experimenter. But why think that those words are meaningful as the axes defining our geometrical space of smell experience? So one thing you could do is use a data analysis technique. So the general family name for these techniques is multivariate analysis. There's lots of different kinds. Ones that get used in psychophysics have names like multidimensional scaling or principal components analysis. And what you do with these is you try to compress the dimensionality of the data set using different algorithms, such that you're still preserving the relative distances between the data points. So you think that the high dimensionality of the data set is kind of irrelevant. You're trying to find the real structure as the kind of minimal representation that preserves all the relative distances. So for the case of MDS, this is a diagram that I came up with to try and use a toy example to show how that might work. So over in the left, you've got you've got 4 data points in a 3-dimensional space. And what the multidimensional scaling algorithm kind of does is sort of like stretch the cloud of points in a way that preserves the relative distances. So AB, AC, CD, CB, BD, the ordering over these relative distances stays the same as you stretch that cloud of points. But then as you stretch it, you kind of remove one of the dimensions, and you can project what's left down from 3 dimensions into 2 dimensions. So I don't know if that helps to imagine how a procedure like that might work in 146 dimensions and gradually reduce the dimensionality of that space. The actual technique I'm going to talk about, well, I'm not going to say any details about it on the next slide, but the actual technique used in the studies I'm going to refer to wasn't this exact one anyway. But this is just to give you a qualitative feel of how you might manipulate data to reduce its dimensionality. So there's a study that took this Dravniak's data set and did something sort of similar to this. They used a technique, they actually used principal components analysis, but one which tried to find a kind of underlying structure that preserved the relative distances. And they found out when they squished things down to 3 dimensions, there was this kind of, they call it in the paper even, a potato chip surface that accounted for 54% of the variance of the data of the relative distances. And if they looked for the kind of analogous potato chip space, such shape space in 10 dimensions, they were able to account for 90% of that variance. So they're able to reproduce the relative distances between the points from the original data set with 10 dimensions. And remember that I said, for me, convergence using different measurement techniques goes a long way towards telling you you've really latched onto something about the world. And for me, it motivates the kind of move to some sort of realism about the space that you're studying. There is a different analysis of the same data set, but using a different technique to analyze it, that also found 10 dimensions captured most of the structure in that original data set. So maybe this is all very fast. We can talk about it in the questions. I want to leave lots of time for the questions, so I won't go on too much longer. But why think, so I've just said, okay, here's a cool data set of smell experiences. Here's a manipulation of that data set that looked like it produced a 10-dimensional model. Why think that smell might have as few as 6 dimensions? Well, first, it would be very surprising if the quality space for smell experiences had as few as 6 dimensions. There are lots of reasons that have been published for thinking that there should be many, many more dimensions in that. So there's an influential paper from 2014 that tried to argue that humans should be able to discriminate more than 1 trillion distinct smells. And if you contrast that to there being only 2 to 7 million colors that people are thought to be able to discriminate, depending on how you analyze things, it looks like smell space should be way larger. And one way that it might be way larger is by having many more dimensions. Another reason you might think that smell space should be super large is if you think about the physiology. Again, in the case of color, there are 3 cone cells that analyze the light coming into the retina in terms of 3 dimensions of color, arguably, whereas there's approximately 400 odor receptors. And there are good reasons to think that there isn't a one-to-one correspondence between odor receptors and dimensions of phenomenal smell experience. But still, with lots and lots of receptors, you might think there should be a really complicated, large space of phenomenal experiences of smell. And this paper, Young et al., is written, co-authored by some olfaction scientists, and including, for full disclosure, at least one who was also a co-author on this Bushid paper that I mentioned, and the philosopher David Rosenthal, who's probably the most famous person for talking about quality space theory in the philosophy literature. And they don't put a number on the number of dimensions they think smell space should have, but if you look at the kind of argument they make for how you might calculate that number, it looks like it should be super big, maybe hundreds of dimensions. Okay, so just to remind you, applying this criterion for successive convergence, if you had multiple data sets, maybe multiple methods of data analysis or methods for constructing a concrete representation of smell quality space, and they converged on structures with the same number of dimensions, and ideally ones that where somehow you had reason to think that those were somehow equivalent spaces, that they could be kind of rotated into each other, something like that. That, for me at least, would count as evidence that olfactory experience had that many dimensions. So is there something like this? Well, the same gentleman, Kolakov, who I showed you his 10-dimensional analysis of olfactory space looking just at the Dravniak's data set, has a later analysis using similar kind of statistical techniques, but now applying them across several different data sets. So each of these, if you look at the graph here, FlavorNet, Valsall, Good Sense, Arctender, Dravniak's, these are names associated with different data sets, each of which is sort of similar to the one that I showed you insofar as it has a list of words, of descriptors associated with different physical stimuli for smell. And what you see here is their initial value, where they're trying to see how many dimensions they needed to try and capture the relative distances in these spaces. And that's the number at the bottom here. And one thing you notice is Dravniak's, which is the black line, shoots up to capturing most of the distances near 10 data points, 10 dimensions, which is what we saw in the previous analysis. The Valsall data set kind of immediately goes all the way to capturing all the variants. What they say about this is a data set that collected smell descriptors not from people who are professionals in perfumery or olfactory scientists, but just from ordinary people. And what they say is essentially that data set turned out to be basically one-dimensional, because most people, if you ask them to describe a smell, their subjective sense of their hedonic sense, is it a pleasurable smell or a disgusting smell, just dominates everything else. And the words they use so that's really got just the hedonic dimension to it. But the other data sets, they're adding in many, many more dimensions, and they're still having a hard time recovering as much of the distances as they did with the Dravniak set. So what do? I'll see if I can describe it so that it makes some kind of sense. This is how I understand what they're doing. They say, well, wait a minute, maybe what's going on is there's kind of outlier smells here. There's particular smell stimuli that create really strong associations. And so people say really specific things about them. And then that kind of like forces you to have more dimensions just to include them within the space. But that's really more about the kind of strong emotive associations we have with smells than really the dimensionality of our phenomenal space. So they leave the outlying data points out in order to redo their analysis. And then they suddenly get 6 dimensions. Looks like it really captures most of the distances in all of these data sets. So how do you make sure you are not really leaving something important out? Well, what they then tried to do is reconstruct the descriptors for the guys that they left out. And so it turns out that they do pretty good at reconstructing the descriptions of volatile molecules, where they flatline their performance on that, again with 6 dimensions. So there's a sense in which there's a kind of convergence here. They're doing the same kind of statistical analysis, but they're doing on a set of different data sets, and they're getting which have been collected using different stimuli and with different sets of subjects, and they're converging on a 6-dimensional smell space. I'm going to end here because I want to make sure that there's time for questions. So I'm going to skip this. I just want to briefly say this is an attempt at a 3-dimensional representation of olfactory space that's, again, motivated by the perfumery tradition. It's looking at a lot of data. It's looking at the same data sets that other study was looking at, but it's really focused on getting something that's 3-dimensional. What's interesting about this study is it's a very different kind of study. And of course, it's already deciding it's going to come up with a representation that's 3-dimensional. But if you see those dotted lines that are coming out of it, those are 3 different cases where there was an aspect of experience that they really would have needed a further dimension for, and they kind of suppressed it. I say 3, even though there's 4 dotted lines, because actually, if you look, there's 2 associated with the qualitative experience of sulfidic, the one at the bottom, and the one kind of associated with garlic and onion. So I don't know, maybe I'm distorting what this study says, but I think that's really like one dimension that kind of like interacts with the 3 representations at 2 different places. But if I could convince you of that, then it would start to look like this was independent evidence for 6 dimensions, because they held themselves to a 3-dimensional representation, and they acknowledged there were 3 further dimensions they really would have needed to capture the kind of full richness of smell experience. So in the interest of having time for questions, I want to conclude and say first, so I tried to show you that phenomenal quality spaces can be measured, and thereby phenomenal experience can be studied in a rigorous intersubjective scientific manner. Smell is really tough. It's a lot harder than color. In the philosophy of mind literature, there's been a lot of ink spilt on color as if it's especially difficult, but actually it's certainly the easiest secondary quality to study scientifically. These kind of mathy techniques that I didn't really tell you very much about, I just showed you the picture of for reducing high-dimensional data, can actually be applied in a fruitful way to take complex data sets about smell stimuli and try to produce geometric models of smell quality spaces out of them. And there's some very limited results that I'm kind of reading between the lines here, but that seem to surprisingly indicate that our smell experience may have as few as 6 dimensions. So thank you guys for listening to me. Let's see if I can stop sharing my screen here. Oh, I'm dark. Wait a minute.